All right, so we got about 1 minute before the class starts, and I'm going to guess today's focus, or at least the first focus, is going to be the Fibonacci program. Not really sure, I haven't really checked how many people have turned it in, and of those people who turned it in, I'm not really sure how many of those um, are working. So I'm going to go over not only the solution of that homework assignment, but I'm going to do it. I'm going to write the program live, just so that you guys can see the approach of doing it, and hopefully some of that is applicable to the program that is due tomorrow. And I'm also hoping that most of you have at least gotten started with that other program. So that's kind of the plan for today. And then tomorrow we're going to talk about the solution of the program that's due tomorrow. Um, Maybe I'll flip the order around. Maybe tomorrow we'll talk about the practice final exam, and then if we have time, then we'll go ahead and talk about the solution of the homework, because that will leave us one more day in case anyone has any question about the topics for the final exam. The final exam is going to be our last day of class meeting, which is on Thursday. So on Thursday at 5:30 p.m. is going to be the beginning of the final exam. It's going to be 2 hours long, so that means it's going to go from 5:30 p.m. to 7:30 p.m. There will not be any lab after the final exam. All right, well, it's time to get started. It's 5:31 almost. All right, so we're going to get started with the program that's due in just about a minute ago. And this is the program. This is the Fibonacci program. And particularly, you are responsible to write this code or translate this code into assembly language. In the process of doing this, you'll be reviewing a lot of material, including how to access parameters, how the stack is organized, how to call, how to return, how to implement conditional statements. Even though this is a ternary expression, it still has all the elements of a conditional statement. There will be a question of how do we call a subroutine, even though this is recursion. Now, recursion is no different from just calling any other subroutine. You still have to do the same thing to push the arguments on the stack, push the return address, continue execution at the subroutine, and when we come back, we have to deallocate the argument. The trick of this particular program is we have two calls. So we have one call with n minus 1 as the parameter. We have another call with n minus 2 as the parameter. So each one is pretty much standalone by itself. But the problem is, where do you put the return value after the first call is done? Because after the first call is done, the return value is going to be in register A. But you cannot count on any registers, not register B, not register C, to retain its value when you are calling a subroutine. That is not a part of the caller-callee agreement. So the only place that is safe for you to store the return value of the first call is on the stack itself. Okay, so the sample program that I was talking about as a clue, which is in the assignment or in the lab of parameters and return value, I think that one, is it uses a trick that is really useful, which is pushing it on the stack and then retrieving it from the stack when we need it. So when we get to that point, I'll explain that. All right, so let me just pause and see if there are any specific questions about this lab that I can answer right now. Anything that is conceptual that I can answer right now before we actually dig into the code. And Paul is asking a question. Excellent. All right, so the question is there a strategy for that use of the stack that is substantially different from introducing a local variable in the subroutine? It is different in the sense that if you declare a local variable, the local variable should be visible and should be alive, quote unquote alive, which means it continues to use stack space, at least within the entire scope of that local variable. Um, and obviously that is there's something that when the program is written in C, it is something that the C programmer has to track and make use of. And in this sense, the original code does not have a local variable, and as a result, it is up to the compiler. Normally, it is up to the compiler to decide, oh, okay, I need to save something on the stack, and it would just kind of stash it on the stack. The compiler automatically makes use of the stack for a lot of things, because anytime you want to save the value of something, the stack is really the safest place to save it. Um, so from that perspective, you can use a local variable to get around that problem. It would be quote unquote equivalent to pushing the return value on the stack. But in this case, it is what we store on the stack has no name to refer to. It is simply the item that was pushed earlier on the stack, as opposed to local variable blah, in and in the case of an actual local variable. Not really sure whether I answered Paul's question or not. Okay, sure. All right. So I'm I just want I just want to check to see if there are any additional questions before I get started, because once I get started, there'll be a lot of detail to track. And also for programs like this, it is probably a good idea not to write the entire code all at once. So I'm going to illustrate that aspect of writing code in small steps as well. So today's lecture is going to be a little bit tedious because I'm going to force myself to make slow progress. Only maybe write 5-10 lines of code before I stop, check, and then go back and add some more. All right, I don't see any additional questions. I'm going to get started then. All right, so the main program of this, I might as well just kind of write the entire thing. I think I gave you guys the main program code, um, but there's no need to, copy and paste, from my own code in the past. So I'm just going to write the entire thing from scratch. All right, so I might even have it still here because I haven't rebooted my computer since that time. Let me see, is it Recursion? Let's see. That's a different recursion. Okay. Although it does look awfully close to our program. Let me look at the C code. There we go. Alright, well, it's pretty close. As far as main is concerned, it doesn't make any difference. So I can just kind of hijack the main from this particular program and just change the definition of F. Okay, I thought I saw someone typing in the text channel earlier, but there's no new text. Okay, never mind. Alright, so the only difference is the type of the return value and the type of the parameter, and also how we are going to structure the inside of F. And I'm going to do it my way first. I think I understand what Paul is doing. Paul is probably using a local variable and converting the ternary expression into a conditional statement. That's my guess. But I'm going to keep using my way of doing it first, and then we're going to take a look at the other approach if we have the time. Alright, so if x is less than 2, then we just return the value of x by itself. No need to do recursion in that case. Otherwise, we return the value of x minus 1 plus the value of x of f of x minus 2. So instead of using n, I'm using parameter x here. And then main, I can just keep it the way it is. Instead of using x, I'm using p. So the program is, for the most part, identical to the one that I have in the assignment. All right, so let me save that. So I am overwriting recursion.c and recursion.ttp ASM today, but the one from before is already posted in one of the text channels. So if anyone wants to go back to the old version of recursion, you can always go back in the previous text channels to locate that one. All right, so a few things we need to do is to most of this we don't have to change because the only difference is we don't have a local variable v anymore. So v is gone, and then the return address is exactly where the stack pointer should be pointing at the entry point of the subroutine and after everything is quote unquote allocated. In this case, there are no local variable to allocate, so otherwise, the math still works out because x as a parameter is still sitting at one location that is higher than where the return address should be found, and the stack pointer should be pointing to the return address on the stack. So let's go ahead and write this code. So I'm going to locate line 16 and I'm going to delete a whole bunch of code until we get to the return statement, which is all the way down here. So line 13 to here, delete. And we don't need to allocate for local variable. There are no local variables in this case. So this is what the stack should look like at the entry point of the subroutine. And let me check the text channel and make sure I'm not missing any questions. Nope. Okay. All right. So now our focus is really just focusing on the code here. And as I said earlier in the previous class, the first thing we need to do is to make sure that we can indeed access the parameter correctly. So the first thing I'm going to do is to use should be a very boring but well understood approach at this time. So if you're not fully understanding what these instructions are doing together, you probably want to either concentrate and focus on the way I explain it, or you can also track the trace analyzer, because the trace analyzer does visually show what is happening with the registers and also memory locations. So the first thing we do, or I do, is to load the offset to find parameter x into register A, and this is just an offset which is literally just 1. Okay, so register A now has a value of 1, which is not particularly helpful. But once I add the stack pointer, which is register D, to A, now I have the stack pointer plus 1, which is exactly where I'm supposed to find parameter x. So one thing you can do is to write this code in sections. In other words, I'm just going to halt here. Okay, if I want to test this program, I'm just going to halt here. Not really a whole lot has been done, but at least I would be able to verify to see whether register A now has the value. Excuse me, I take it back. Now has the address of parameter x. And at that address, I should find the value of 3 because that's what the main code is supposed to have pushed on the stack. So I'm just going to stop here. Okay, I'm going to save the program and then go to my reverse spider. This is the private one where you guys cannot see. I'm going to use the one where you guys can see. So we'll go to the one where you can see. This is the public one in the shared folder. So if you want to, you can go to that particular spreadsheet so that you can navigate to wherever you want to go to look at things. Okay, so I'm just going to run the program here to submit recursion. Oops, recursion.ttp ASM. There we go. All right. So at this point, the trace should be either in progress or it should be done. So now we're taking a look at that particular spreadsheet. I just keep mine open, always open in a tab because I use it so often, and it's very good to see many people, well, too, are also getting there to take a look at the analysis. All right, so the analysis tab is still working. All right, there we go, it's done. So we want to kind of, well, this program is really short at this point, okay, in terms of how much code is being done. So we can actually track this, just manually. This is where we initialize the stack pointer to 0, 0. This is where we allocate for the local variable p, in this case in main. And then this is how we initialize that location to a 3. Okay, now I'm getting a little suspicious because ff is supposed to be where the parameter is stored. Let's see. Nope, I take it back. Okay, I take it back. Sorry. So ff is correct. Okay, d is decremented to ff to allocate for the local variable p in main, but I'm not going to store anything into p until I get the return value of calling f. So the next two statements, the next two instructions, is initializing register a to 3, and then storing the 3 on the stack. This is really just pushing 3 on the stack as the argument. Okay, so because before we call a subroutine, all the arguments need to be pushed on the stack. The stack is the only place and the only way for a caller and a callee to communicate using parameters. Once the argument is pushed on stack, the next thing we do is to get the return address, which is at location 16, decrement the stack pointer, and then push the return address on the stack as well. This is how the subroutine knows where or how to get back to the caller. And then at that point, the control is passed to the subroutine, and we can see that by looking at the more or less sequential PC program counter. So it goes from 10, 10 to 12, 12 to 13, 13 to 14, and then suddenly it went to 03. That's because we have a JMPI to F at that point. So 14 is a JMPI F in the TTPASM mnemonic. When we continue execution at location 03, which is the first location in the subroutine F, I can see from the side effect that I'm loading a 1 into register A, which is loading the offset of where to find the parameter on the stack. And then we add the stack pointer to A, okay, to register A. The stack pointer is FD at this point, so when you add 1 to FD, you end up with FE. And I claimed that FE is the location of where we can find the value of the parameter. So if you just kind of track, how we modify RAM in column C, you can see the last time we modified location FE was to put 03 into it. So that means, at this point of time, at location 05, which is right after the add AD instruction, register A did, in fact, have the address of parameter X in this case, because I changed the name of the parameter from the lab, so I have to readjust the name of the parameter. So at this point, okay, so at this point I have confirmation that the very short program that I have written at this point is indeed correct. Okay, so that is really important because until I can confirm that I can get to parameter X, it really makes no sense to write any additional code because then I'll be comparing and working with possibly the wrong item on the stack or somewhere else. So now I can, put some additional code here. Now, if you are familiar with revision control software like Get or SVN or CVS or RCS, all of those are what we call revision control systems. Some are really easy to use, like RCS is completely easy to use as a for a local directory. Get is pretty easy too. You can actually use get, git, in a local folder. I'm not going to teach you guys how to do that because it's completely optional, but it really is helpful if you want to track how you have changed the program and you want to label major landmark versions of your program because you got a certain major thing done at that point. So this way, if you ever did something later on that made the program not work anymore, and it's mysterious to you because you have no idea why it's no longer working, you can use revision control to go back to compare the current version of the code to any previous version, and it will show you the diff. It will show you the differences between the current version and the version that you have checked into the repository before. So it will highlight all the changes, and there probably should not be a whole lot of changes that you have made, and it would be easier this way for you to figure out, oh, okay, I made this change, and it's not a it's just a careless mistake, okay, but I did make that mistake. It's easy to spot problems that way. Anyway, now we move on because according to this code, we are not interested in the address of x. We are interested in the value of x. So we're going to do a LD AA. So right now, register A should have the value of parameter A. I'm going to sound like a broken record, but I'm going to do it anyway. So after this session, it is going to be quite helpful, especially for people who are a little bit dazzled by this program, by this homework assignment, to go back in and then comment every single instruction to explain what it is doing and why it is useful and how it relates to the original program in C, because that is going to be, I think it's going to be very useful. So there's that. Okay, so at this point we do have the value of x in register A. And the first thing we want to do is to compare that to 2, because if x is less than 2, then we want to do one thing. If it is greater than or equal to 2, then we want to do something else. So we're going to do LDI B with 2, and then we do a compare. Okay, so now the question is, which way do we want to compare? Because you can do a compare AB, you can also do a compare BA. Okay, so now that we have a choice, we're going to have to evaluate each choice and figure out which one makes more sense. So since we only have the ability to detect whether it is equal to or less than, and in this case less than is what we want, so we want to see if register A, which has the value of x, is less than the value of register B, which is now 2. So it makes sense to do a CMP AB. And next we have to use a conditional branch instruction to see if A is indeed less than B. We're talking about registers. And because x is unsigned, so that means we have to use unsigned comparison. So this kind of goes back to the flags, because we have 2 flags that can indicate whether the minuend, which is the first register, is less than the second register, which is B in this case. One is the carry flag, which is also the borrow flag. The other one is the L flag, which is basically the exclusive OR between the sign and the overflow flag. So in this case, we should use the borrow flag, but there's no JBI, there's only JCI. Okay, so we should use JCI in this case. Well, so I'm pretty sure someone is already asking, what if I use JLI or JSI or some other flag instead? So I'm going to tell you 2 things. One is for the range of value of x in this program, they may not make a whole lot of differences, because we can't really have x going up to a high value simply because we don't have that much space on the stack, and we don't want to wait for the program to finish, because the amount of time to run this program is exponential to the value of x. So that means technically, if someone was to use JSI or to use JLI, because it will never overflow to begin with, the program will still work. But now the question is, what is TAC going to do? TAC is still going to look at JLI and say it is wrong. okay? Because it is wrong because it is conceptually wrong, even though in this case, the program will still run exactly the same way without any problem. So now the question is, but why is it considered wrong if it will still work in this case for all the conceivable value that we can put into X? It is because if this program is translated into a different architecture, and we do have room and also the time to run it, beyond a certain range, then the program would be wrong because it simply would not do the right thing anymore. And in the class like this, it is the concept that counts. It is not whether the program quote unquote works or not. It is whether the program is right or not, whether it's correct or not. Not correct only in certain cases, but correct in all cases. Okay? So I would still consider JLI as the wrong instruction to use. Not majorly wrong because the program will still be able to produce results in many cases, but it will still be conceptually incorrect. Sub would still be okay, as long as you don't need to keep A around. That's the only difference between sub and CMP. Is sub does change the first register, where CMP does not change the first register, which means it becomes very easy for me to use it again. So either way is fine. And then JLI is, once again, not the best way to do it, but it will work in this case. So I'm going to do the right thing, put it back into SJCI. And then we are going to say JCI, and usually it is a good idea to label the branch or the label based on what it means. So we're going to say F underscore X is less than 2. Okay. I'm just using these names. I mean, obviously you're free to choose whatever label you want to use, but I prefer that my label, to be at least, self-documentary to me. So now, if it is not less than 2, this is the actual else branch. Okay, so I would just say this is the else branch. There are several ways to do this. You can always do a JMPI to the else branch and then label this one as the then branch. That works too. Okay, it's just a matter of preferences in this case. How large of a value of X would be possible to evaluate in this case? Okay, so remind me to get to that point later on, because it depends on how much space in the RAM is being used up for the code. Yeah, so just kind of remind me to go through the analysis. So I'm going to try to make this program short so that we have more space left to have a deeper recursion. Okay. All right. So at this point, I'm just gonna I'll just put the else branch here. Now, if I do put the else branch here, I still need a JMPI at the very end so that we can continue execution at the right place. Now, it all depends on the optimization, because if I structure this correctly, I could potentially not to have a jump around, okay? But that relies on me putting the correct value into register A at the very end of the else branch, okay? So I just have to be careful, okay? That's all. So at this point, okay, register A already has the correct return value. So we are pretty much done at that point, okay? Meaning that I don't have to do anything special to put the return value into register A, because I got to this label because of the JCI, and also because the JCI would not have occurred until I already have the value of X in register A, which is exactly what I want to do when I get to the then branch of the conditional statement here. Okay, and if I really want to emphasize, I can also kind of write down the comment here to make sure that I remind myself that I reversed the position of the else versus the then branch in order to save a few branches, a few JMPI instructions. Okay. All right, so now into the else branch, which is the difficult one. Okay, so we do one thing at a time. We focus on only one thing at a time. So right now we just want to push x minus 1 on the stack and then call f. Okay, which is pretty easy to do because register A already has the value of X at this point. So all we need to do is to decrement A, decrement D to push it on the stack, stda. So at this point, we should have pushed x minus 1 on the stack, and then we just have to call f at this point, which is the same sequence of instructions no matter where you're calling f. So we have ldi a dot 6 plus decrement d to allocate a byte on the stack to store the return address and then actually store the return address. So now that we have the return address pushed and the argument obviously is already pushed earlier, we can do a JMPI to the subroutine that we're calling, which just turns out to be the same subroutine that I'm in. It doesn't change a single thing. The pushing of the argument is still the same. The pushing of the return address is still the same. When we get back, it's going to get back to the instruction right after the JMPI instruction, and that's because what expression we use here to initialize register A, because that's the return address. The return address is the address of whatever opcode that is right after the JMPI instruction. So when we get back, we have one item on the stack that is not useful. So we're going to do an increment D to get rid of the argument that is still sitting on the stack. So now we have to be careful because we have to think about what are we going to do with the return value of f of x minus 1, which is sitting in register A at this point. Okay. And if you recall what I said earlier, the safest place to stash something and you don't want a subroutine to mess around with it is on the stack. So we just have to push register A on the stack at this point, which is going to look silly, okay, because we are decrementing D, we are incrementing D, and then we decrement D again. Now, it is important, even though as much as I want to optimize the program, I will leave these two as is, okay? You can comment these two out because they cancel out each other. The reason why I'm leaving these two here is because the increment D has to do with deallocating the space of the argument, and then the decrement D has to do with pushing the return value on the stack. In other words, even though they seem to cancel each other and they seem to be very related, the context in which each instruction is needed, that generates the need, are completely different. Okay, one has to do with the argument, and that's something that we have to do after every single function call, is to deallocate all the arguments. The other one has to do with, hey, this register A is something that we will need later on. Let's stash it on the stack. So that's why I will leave the two instructions in the program at this point. And we got Fooling asking, is it right? X return address. Yes. So in the text channel, Fooling is correct that X is at the highest address, and then return address is 1 byte below that, and then the return value of f of n minus 1 is 1 byte below the return address, or the byte that stores the return address. That is correct. All right, so at this point I'm going to say, okay, wait, hold on a second here. I'm not really sure this program does work. Okay, so let's halt. Okay, so now I actually have written too much code already because I have the conditional part and then I have the recursive part, at least the first part of the recursion. So when I test this code, I'm going to have to select my values. I'm going to run it several times, and then each time I'm going to use a different value of x just to test whether a particular part of the program is working or not. Okay. So this is another thing that is really useful when you are debugging a program, is not to use a complex test case to begin with. Use simpler test cases. So in this case, the two simpler test cases would be when x equal to 0 and when x equals to 1, because it is not supposed to have it's not supposed to do the recursion in those cases, and which means it's going to bypass all of this code here, and it's going to get here, and it will hit the other halt instruction, which is fine, okay? Because when it hits the halt instruction here, it is still, we should still have the return value of that invocation in register A. So I'm going to test the program. Now, before I test this program, I'm kind of have to go to main and change the argument that I'm pushing on the stack, because I need to change this to a 0, because this is the argument to call f. Alright, so now that I have changed the main program to only try to find f of 0, which should work because it doesn't need recursion, we'll go ahead and test the program. Okay, so we'll go ahead and resubmit the program. Alright. Okay, so the program has changed a little bit, and the execution is going to change a little bit too. Now it's going to be longer because we have moved the halt instruction. Effectively, we have moved the halt instruction down quite a bit. So 0 is pushed on the stack. This is the new return address to main, and then we continue execution in the subroutine F, and we should retrieve the value of the argument right here, and then we compare that to 2. And then we have the conditional branch. The conditional branch should branch, okay, and we can see that it is branching because we went from 0A to 19, which is where the halt instruction is. So by the time the program got to the halt instruction, register A has a value of 0, which is correct because it does not do any recursion when the parameter is 0 or 1. So the other thing we can do, okay, going back to the source code, is to change the argument from 0 to 1, because it should have an identical trace, except that register A now has a value of 1 instead of 0. So now that we have changed the source code, we just have to rerun the whole thing, reassembled, blah blah blah, okay, and now we get to the new trace, and we can see how register A ends up with a value of 1. Okay, so the program does work correctly in both cases. So now we have to ask a question: what if we are to change the argument to 2? Okay, so let's go back to our source code, and then this time we change our argument to 2. So this time you can use the C code too. By the way, you can use the C code to find the behavior of the C code by just changing this f of 3 to f of 2 and then single step through the program. Okay. Okay, we got a text channel here. Doing this without the script was very fun. Well, that's how I have been doing this for years. This is the first semester I have the actual script to do this without having to just do a whole lot of import and so on and so forth. So this is the first semester for me to have this convenience of not having to do everything manually. When I said for years, I'm talking about maybe 4 years or so. So every year I add a tool to this whole thing. I have added the trace analyzer tool for some time, and this is the first time where I have an actual script to automate some part of this process. But Curtis is correct. It is tedious to do it without the script. Nonetheless, it is still doable. All right. So what was I saying? I got distracted. Okay, the program is changed, but I have to rerun the trace. But we want to find out what it is supposed to do, okay, before we actually run it. So let's go back to the source code and find out what it is supposed to do. So when the parameter is 2, it is not going to do the JCI because A is no longer less than B, and as a result it will just continue execution. So that means it's going to decrement the 2 to a 1 and then push it on the stack and then call F again. So it will have one recursive call of f of 1, and then that recursive call is going to go through the same branching and then hit the halt instruction down here. Okay, it's gonna. There are two halt instructions. You kind of need to know which one we should be hitting, because this time we should be hitting this the same halt instruction as the first time, because the subroutine will never return to get to the first halt instruction. All right. So once we understand what the program is supposed to do, let's go ahead and run it. Okay. All right. So now we go to the trace analyzer, and we should see the trace being a little bit longer now. And we can see how A is, 1 is now pushed as the argument of the recursive call. This is the return address back into F itself. And then this is the second invocation of F, and trying to check whether its parameter, which is 1, is less than 2 or not. And once it compares, which should be this instruction here, you can see how the carry flag is a 1 because it is register A is less than register B unsigned. And by the time we get to the conditional branch instruction at 0A, it decides to branch because JCI, the C is a 1. And then we end up at the halt instruction at location 19, which is exactly what the code is supposed to do. All right. No questions? Well, how about this? I'm going to give you guys a little bit of time to think about what we have written so far and see if there are any questions. So I'm going to switch back to the code. So this way you can look at the code and see if there are any questions. All right. No questions. Okay. So if there are no questions, I am going to unleash function f a little bit by removing this halt instruction here. So by removing this halt instruction, all the non-recursive calls are going to actually return a value through register A. So that means the recursive call from f of 2 to f of 1 is going to return. When it does return, it will get to the increment D instruction to deallocate the argument of 1 from the stack, and then it's going to okay, let me repeat that. It will first deallocate the argument. It's going to reallocate stack to push the return value on the stack, which should be of 1, and then it should hit the halt instruction. So by removing just one single halt instruction, now I have changed the flow of the program to check to see if I'm actually pushing the value of f of x minus 1 correctly on the stack or not. Okay, I need to know what I'm pushing on the stack, what I'm saving on the stack, so I need to double check that. Oh, okay, wrong command here. Okay, so now we're going to rerun the program. So Curtis is absolutely correct. Having this script does make things a whole lot easier, because now we can just rerun the program, pretty conveniently. All right, so the trace is going to change a little bit, right? Because where we saw the halt instruction is going to now do a return. So this is going to fall through, and then we're going to retrieve the return address, and the return address is 15. We increment the stack pointer because the return address is no longer needed on the stack, and then we continue execution in the quote-unquote caller, which is also F, and then the caller is incrementing D to deallocate the argument that is still sitting on the stack, and then it is decrementing D in order to reserve a byte to store the return value of f of x minus 1, which in this case is just f of 1, which is 1, and that location is now storing 1. So that means the code is working up to this point. Okay. So next, I'm going to call f the second time. So let's go back to the code here. And I'm going to make a mistake here. I'm going to intentionally make a mistake just so that, we'll talk about, so that I can talk about, that particular trick, why it is why it's not working. Okay, so now we're going to call the f the second time. Okay, so f of x minus 2. So at this point, I cannot count on register A still having the value of x. I mean, that's a no-brainer, because A is now the return value of x minus 1. So absolutely, we cannot rely on register A still containing the value of x. But that's no big deal, right? Because we can just redo the whole thing. Just get the offset of x into register A, add the stack pointer value to the offset. Now we have the address of x in register A. Do LDAA. Now we have the value of x, and then we'll go ahead and push it on the stack because we are trying to call f the second time. And then we just do a decrement D, stda, and then we do the return address, LDIA with dot 6 plus, decrement D again, stda. Now that we have pushed the argument and also the return address on the stack, it's time to call the subroutine recursively. So a JMPI to f again. When it does return, it should be here right after right after the JMPI instruction. This is where I need to do an increment D to deallocate the argument. And at this point, register A should have the value of f of x minus 2. The stack pointer should be pointing to the saved value of f of x minus 1. So I'm just going to halt here, because before I say, okay, I'm done with the recursive case, let's check it first. Okay, so we're going to check it. Okay, so we'll save this file, and I'm going to keep using f of 2. So main is not f of 3 at this point, it's just f of 2, because in this case it should calculate f of 1 and then f of 0, and we'll see whether that works or not. Okay. And obviously, I already said that I intentionally make a mistake here, so that means this is not going to work. The question is, how do you check whether it is working or not? So we're going to redo the whole thing, get a new trace, and find out whether it is working or not. All right. So now we get back to the trace. So last time, we got back to here, and then we got to the halt instruction, right after. So this time is going to be a little bit different, right? Because it got back to the call, and then this time we're going to call it one more time with f of x minus 2. Okay. So we load the offset of x as a parameter into register A, and then we add the stack pointer to register A. So now it is FD. Then you go like, but tech, wasn't it FE before? Yeah, it was. Okay. So once we do the LDAA, A is now 36. Then you go like, we should never be trying to compute f of 36. We're supposed to be doing f of 0, not f of 36. So now we know the program is not working. Okay, something is not right. Specifically, when we got to the address of x, it is not right anymore, because the address of x really should still be FE and not FD. Because this is still in the first invocation, we have returned from the second invocation already at this point. This is the first invocation of f, where the parameter should be at location FE and not FD. So the question is, why is it at FD? What else is sitting on the stack? Now, if you just go back to the text channel in Discord and get to what Foolin has shown at time 6:01, I think, now we know, because the stack pointer is no longer pointing to the return address. It is now pointing to 1 byte below the return address. So all the offsets, when I said all, that's only one, but all the offsets that we have labels, to to remember using a symbolic name, they are all off by 1 now. Oh, okay, so that is why the address is off by 1, because the stack pointer is pointing to 1 byte below the usual reference point that we count on when we define the symbolic names of f of x. So this is the tricky part where you have to go back to the code. There are several ways to fix this problem. The easiest way is simply to say, hey, this label f of x is 1 byte off. We need to add 1 to this offset because the stack pointer is now pointing to 1 byte below where it used to be. So to compensate for that 1 extra byte that we are using on the stack for the return value of f of x minus 1, we now need to say, everything is now off by 1. Okay, no big deal, we can do this. Because all we have to do is to say the offset that used to be 1 is now 2. I'm going to pause and see if there are any questions about this. All right, so okay, I'm gonna give partial credit, for this particular program. So hopefully, you guys turn in something. By doing that, I'm gonna kick myself later too, Curtis. So you're not gonna be the only person who's gonna kick yourself. I'm gonna kick myself too. Because if I'm going to do partial credit, for programs that do not run, it's going to take a long time to grade because I have to read the code, find out why it is working or why it is not working. Is it close? How close is it? And so on. So, yeah, that's gonna hurt. We got 2 more people typing. Okay, so we got Abdullah, saying. So we thought that SP to f of x, but it was actually pointing to. Not sure. The stack pointer is pointing to the saved value of f of x minus 1, if that's what you meant. That is correct. So x is 1 byte on top of that. So all the offsets are off by 1. Yep. All right. Okay, so all right, cool. So if this is making sense, it's great. Okay, as a homework assignment, as a lab, it's only 4 points. It is 4 points out of all the points of all the labs and all the code that you have written in this class. In other words, not really a whole big of a dent if you were to miss this assignment, miss this coding assignment altogether. But what you're learning in this process, even if your program doesn't work, okay, and you look at my code and go like, man, darn it, now I understand what it is. It's still worth it, okay, because in the final exam, which we'll be talking about tomorrow, it really requires people to understand the code and not just going like, oh, I can copy and paste the code, because it's not going to be you coding, it's going to be you debugging, okay, which is kind of interesting. So we'll get to that tomorrow. At least what I did last semester. Okay, what kind of a final exam the class got last semester. All right, so what I'm gonna do now? Guess what? I'm not gonna write any additional code because I think I just fixed a problem. It is important to verify that I did in fact fix the problem. In other words, once I fix this and I get back to the trace, this should no longer be a 36. It should be 0, okay? Because I should be accessing, oh wait, hold on a second. It should be 2 because I forgot to decrement it, because in the assembly code here, in all the excitement, I decided to just get the value of x, which is 2. So I need to decrement it. But guess what? I am going to, well, let me see. If it's yeah, I have to do the decrement because otherwise the program is going to be infinite. Do you guys want to see how it's going to be quote unquote infinite? Because I make this mistake. Let's do it. Let's do it. Let's just make the program crash even harder. I caught my own bug. Let's just run it as it is, okay? And then and then I'll fix it later on, and then we'll continue with the program. Uh, this is 60 megabytes. That's a lot. Well, this is why in the submit, I think I put a timeout. Yeah, so it's gonna do a timeout in 15 seconds, which depending on how fast your computer is. For those of you with a gaming setup, that can still go really really far. I don't have a gaming setup. Mine is it's just a little wimpy laptop computer that's already 3 years old. So I don't think it can go too far in this case. But you know what? It doesn't really matter. All I have to do is to wait 15 seconds for the trace, and it will still give me what I need to see in the trace analyzer. All right, so there we go. It's just that the trace analyzer, the Google Sheet, is gonna have a field day trying to get this done. You'll see all the loading because now the spreadsheet, the table is a lot longer, a lot bigger. Well, it's done. I mean, that's really fast. Oh, okay, so it is really done. Huh. I thought I fixed that problem. So that doesn't seem right to me. Alright, so if it doesn't seem right, the first thing I need to check is the summary and find out how many lines or how many rows there are. There are 2,900 rows-ish. Alright. Okay. So this is still incorrect. I thought I fixed that. Did I save the program first? Let me check. Okay, so this is supposed to load a 2 into register A. Let's see if the trace says I have loaded a 2 into register A. Nope, I'm still loading a 1 into register A. So there's a discrepancy between the code and the trace. That is, oh, I forgot to save. Look at this plus sign here. Yes, I did forget. Okay, fine. Okay, now I have saved it. This is my, okay, I hate to admit it, but this is my favorite mistake to do. Um, basically making all the changes, forgetting to save first, and then rerun the program and go like, hey, I'm supposed to have fixed this. Why is the program still behaving exactly the same way as before? Obviously, if you have a more advanced integrated development environment, this would not be an issue because the program would, I mean the tool would have reminded you to save it first, or it would not be running the program without you saving the file first. Alright, so now it's better because it is a 2, which means I'm retrieving the right value, which so happens to be 2, 2. Okay, so that's no pun intended. This 2 is the offset, the new offset from where the stack pointer points to find my parameter x. So 2 is correct. At that location, we also have 2, which is also correct. But we are not supposed to be pushing x on the stack. We're supposed to be pushing x minus 2 on the stack. So this part is wrong. Okay, so the rest of the program, the rest of the trace is irrelevant at this point because I just pushed the wrong thing on the stack. Okay, so what do we do? Well, we fixed that problem. Okay, because now we have to say, okay, now that we got the value of x, let's remember to decrement it twice. Okay, now if you want to do LDIB with 2 and then do a SUB, A2 AB, that will work too. I just personally, for something simple, 2 decrements are slightly more efficient because it uses 1 byte fewer compared to the other approach. Yeah, not that big of a deal, but that should fix the problem. This time I make sure that I save the file before I run it again. And now we go back to the trace. And this is also part of the reason why I like the script, because if I ran the script, the cursor doesn't change position, which means, I can now, just go like, oh, okay, it was a 02 before, now it's a 00. Cool. Okay. So the 00 is gonna be pushed on the stack. The return address is gonna be pushed on the stack. Now we continue execution in this is a second invocation, okay, on the stack, but it is really technically the third time we call f, because the second time, the second invocation, it has already returned. So over here, we got back to the value of x, compare that to 2. 0 is less than 2, that's why c is a 1. And then we perform the conditional branch to location 29. And then location 29 just goes like, okay, it's time to return because, x is less than 2. And when it does return, we got to the halt instruction. Okay, so this 27 is the halt instruction right after the recursive case. And this is before we did any calculation between the return value of f of x minus 1 and f of x minus 2. So we didn't really do any calculation, but we could verify that register A has a value of 0, 0. This is the return value of f of x minus 2. And the stack pointer is now pointing to the saved value of f of x minus 1. So we can go back and check what was the value that we put into location fc last time. So we just have to scroll back and go like, oh, okay, well, it was indeed the return value of f of x minus 1. So now the question is, what are we going to do now that we have f of x minus 1 sitting on the stack and f of x minus 2, in register A. So now we get back to the source code and go like, okay, so we got a lot of good things happening at this point. We'll go ahead and retrieve the thing on the stack. In other words, we pop the return value of f of x minus 1 into a register. Any register other than register A is going to be okay. So we'll just put it into, say, register B. So now we do a LD BD and then increment D because it's no longer needed on the stack. That's part of the pop operation, is to deallocate whatever you're popping from the stack because it's no longer needed. So at this point in time, we have f of x minus 1 sitting in B, f of x minus 2 sitting in A, and we just have to add those two. So once again, you have add BA versus add AB versus add BA. And add BA makes more sense because after add sorry, I misspoke. Add AB makes more sense because after add AB, the sum is in register A, and that's exactly what we want to return. So, if I were to do an add BA, I will still have to copy B to register A. Then why waste one opcode, right, when we don't need it? Cool. And we have a halt instruction here. I'm going to keep the halt instruction just to make sure that register A ends up with a value of 1 right before the halt instruction, because then I feel comfortable that at least I can deal with f of 2. Okay, so that's what we're going to do. Make sure the file is saved. There we go. The plus sign is gone, and then we rerun the script here. So you can see, I'm not just writing the entire program all at once and then just be done with it. I'm writing the program in very small segments and then use the tools that we have available just to make sure that things are working correctly. So we can now see how register A has a value of 1 right before the halt instruction, and that is the correct return value of f of 2. How do we know this is the right value of f of 2? There are several ways to do this. You can look up the Fibonacci sequence, and you can see that f of 2 has a value of 1, you can also just run the C code because the assembly code is supposed to mirror the logic of the C code. So they should come back with exactly the same result. All right, so this is all looking good. So now we just have to go, let's finish this program, okay? So if we are to finish this program, we just have to get rid of the halt instructions. There are 2 of them, and just let this code fall through to quote unquote the else the then case. But it's really not the then case anymore. It really is just, oh, this is the way we return, because by the time we get to this point of the program, register A should have the return value already. So that's why, it really is just a merge point for the 2 branches. And then we just return to the previous invocation. And if I unlock that portion, getting rid of the halt instruction, then the main the first invocation of f should return to main. To right at this point, it increments d, get rid of the argument sitting on the stack. Then we calculate the address of p. We store the value of the return value of f of 2 to local variable p, which is sitting at location ff. So we should store a 0, 1 to location ff in this case. And right at the very end, we deallocate the local variable of main by incrementing d again. So d should get back to 0, 0 at that point. And then we hit the final halt instruction of main in this case. Make sure the program is saved. And then we just go through the whole trace process again. Alright, so now we just scroll down and we see that we store a 0, 1 into location ff just as predicted. That's good. The stack pointer is balanced. It is getting back to location 0, 0 right before we get to the halt instruction. So everything is working at this point. All right, so now let's go ahead and answer Paul's question from earlier. So Paul's question is, what is the largest value we can use, before we basically blow up the stack? So the first thing we need to figure out is how much space of RAM is being used for the opcodes. So we just have to find the last location, which is the halt instruction we saw that earlier. It is at location 3F. So that means the first 64 bytes are being used as the program, leaving us with 192 bytes for the entire stack. So the next question is, what is sitting on the stack? Okay, how do we figure out how deep we can do the recursion? So for that calculation, I'm going to use a text editor to help me. Alright, so we got 192 bytes for the stack. Okay, 1 byte is used by main dot, I think this time we call it p. So it's local variable p of main. And then each invocation of f is going to need 2 bytes for sure, okay? But at certain instance of time, it will take up 3 bytes. So the first byte is going to use is for parameter x. The second byte is for the return address, okay? So there are 2 bytes that are mandatory for each invocation of f. But before we perform the second recursion, it's also going to have the saved value of f of x minus 1. So if we only count that from that time on, it's going to take up 3 bytes. So that means, if we look at okay, so assuming each frame is going to take up 3 bytes, remember the term frame, it is basically the portion of the stack that is used by an invocation of a subroutine. So assuming it's going to take up 3 bytes, so we are now looking at 191, and we can divide it by 3, to just calculate, how many times we can do the second recursion. So that will give us, let's see, 63. Okay, so we can only do up to 63 of these um, of the second recursion. The first recursion is only going to take up 2 bytes, so it's going to take up fewer bytes, but the limit is going to be the second one because the second one takes up that extra byte, so it's going to be the second one that is going to be an issue. But remember, the 63 is also going to be, so by the time we get to the second recursion, x is 2 less than what it used to be. So that would be 63 times 2, um, and then plus the initial value, which is 1. So that would give us, okay, so that's 127 from this perspective. So I know for sure that we cannot do 127 because before we get to the before we get to the second point of recursion, the first one is going to take up 2 bytes only. So 191 divided by 2 is, I'm looking at the floor of the actual quotient, and in this case that's going to be 85, right? So 85 is really the hard limit because we can't really get to the 127 because by the time we get to the 85, it would be running out of room already. So the answer, Paul's question, 95, thank you. Can't do my math. So the correct answer is 95 in theory, okay? So the amount of time to get to f of 95 is going to be insane, okay? Because the amount of time is exponential. For those of you who have taken CISP 440, the time complexity of this algorithm is 2 to the power of n, where n is the size of the problem. So there's no way we can practically run f of 95, even though in theory it can calculate f of 95. It does no that's just no it's just not practical to try f of 95 in this case because we will run out of time, not space in this case. Yep. Yep. Okay, so there we go. So this is the process of how we analyze the algorithm to figure things out. Okay. The time is 6:41 at this point. So when you're working on the program that's due tomorrow, I'm not going to change the due date because if I change the due date, it won't leave you enough time to study the solution. That's the problem, okay? So we're going to have the same due date of tomorrow, and once again, the point value of the lab is not that much. I'm not saying it is, I'm not asking people to give up. Do not give up, okay? Try your best. Because when you try your best, and then you will still understand a lot of the concepts. It's just that there might be some little things that you could not catch to make the program work 100%. So by the time I explain the solution, everything will click because you have tried your best already, and you already understood the concept. It's just those little things that can cause the program to not to work. All right, so we got a text message. Does it matter if I use reg B to has f of x minus 2 and reg A only for f of x minus 1? That's not going to work either, because when you do the recursion, register B is going to be clobbered by something, by a recursive call, so that it won't work. If you use, it doesn't matter. It doesn't matter which register you use, because the recursive call is going to clobber those registers. You just need to have it deep enough. Anything that's deeper than 3 levels down is going to make any attempt to use a different register to save the okay. Let me get back to this. Why it is not going to work? Because first of all, in theory, you should not be using registers you cannot count on registers to be preserved after you call a subroutine. That is not part of the caller-callee agreement. So in this case, because we are dealing with a recursive subroutine, so that means at some point in the in the future invocations of f, the recursive version is going to think the same way and use register C. And guess what? That is quote unquote your register C that is getting clobbered. So that means using a register to save the return value of an invocation is not going to work. It might seem to work when you use a small value to test the subroutine, but if you try anything that is say 4 or 5, it's not going to work. Yes, absolutely. Use the stack. Yep, the stack is the safest way to do it. And the only way to do it too, because the other way is just not going to work. Um, it just takes a little bit a larger value, f of 5, f of 6, it's almost guaranteed not to work. Yeah, yeah, sure, absolutely. All right, try to use the stack, but don't know how to use. Oh, but ha ha ha. Okay, so let me show you an alternative way to do the same thing. Okay, so let's just say that we're dealing with the assembler before we had these expressions. So how do we deal with that if we cannot do the postfix notation like this? Okay, so if we cannot do a postfix notation like this, the alternative is simply to increment a afterwards. So you're basically using an opcode and using a little bit of runtime, to do exactly the same thing that could have been done at assemble time and not to incur any penalty in terms of runtime. So it's really the same thing, but or you can just put a label of 2. Yes, that works too. Yep. Cool. All right. So we got 4 minutes left in today's lecture. And I use up the entire, all the time to talk about the solution. But once again, I'm not giving you just the solution. I could have just given you a file and just go like, this is the solution. Go ahead and study it, and that's it, right? But I didn't want to do it because I wanted to show you how to write your code in small increments, because that is going to be what you need to do for the assignment that is due tomorrow. Okay. And I also want to show you how to use the tool. Okay, I'm not sure how many of you got this script to work, because there are a few steps, but um, I mean, getting Bash to work in Windows, I think Sigwin could work too. I've never tried it, but the other alternative is to get gosh, I can never remember the name of that thing. It's WSL. Thank you, Paul. Paul can read my mind. It's like, okay, Tech is forgetting that name again. Windows subsystem for Linux. So getting that to work is just an alternative to get it done. 2, yes, WSL2, thank you. So that's the alternative. Sigwind, I have never tried, but that probably would also work. The idea is what tool people want to use is not really my business, even though some tools are better and more effective. So, so if you still want to get those tools working, I still recommend you to look into it, okay, because it might be helpful in the final exam. I'll be talking about the final exam tomorrow, okay, at least, I'll get part of it, discussed tomorrow. Um, I'm going to give you guys the file for the practice final today, um, just so that you have something to practice on. So, so that at least you can get an idea of what it is. All right. So I think I'm pretty much done for today. Oh, okay. You cannot set up the script. Well, the other approach still works. Okay, it's just a little bit more cumbersome. Okay, which is basically go into this tab and re-import the TSV manually. It is tedious, but as I said, this is all I did for the past few years. Okay, so it is not like it's not doable. It's just takes a little bit more time. Um, but other than that, the script only saves you some time. It just shaves a little bit of time from the development. Do you have muscle memory? Yep, that's what I had until Google decided to change the import dialog box. And I go like, whoa, hold on a second here. This doesn't look like what it used to be. Yeah, it wasn't using drop downs before. It was using like a whole bunch of checkboxes and radio buttons before. It's not a big deal. Okay, so I am going to stop the lecture a minute early. This is like a record time. Tech actually finished before the designated time of the class. Okay, um, I'll be back in about 10 minutes or so. Just so that I can see if there are questions about the code that is due tomorrow. Okay. Um, all right. So I'm gonna sign off from the interactive media.